So what's the big deal about moles? Why do we need moles anyway? And what are they useful for? Definition of a mole is that it's the number of entities in 12 grams of carbon-12, or equal to the same number of entities as is in 12 grams of carbon-12. That's kind of an obscure definition. It turns out that if you figure that out, that it turns out to be 6.02 times 10 to the 23rd of anything. Entities, okay? Pieces, atoms, molecules, whatever. And we call that number Avogadro's number because it's such an important number, we have to give it a special name. Now, why would we define this in such a way? The idea is that we've already worked out all these ratios on the periodic table, and we have these ratios that say that hydrogen atoms are 4 times as small as helium atoms, or shall we say helium atoms are 4 times as big, 4 times as massive as hydrogens. Oxygens are 4 times as massive as heliums. Copper is about 4 times as massive as oxygen. And so we've got all these ratios, and if we would just define it in the way that we did, the number of entities in 12 grams of a carbon-12 isotope, that way we can use all of those but just substitute grams for AMUs. And we've already got the ratios all worked out. It's wonderful. And grams are useful to us because we live in a macroscopic world, not in the submicroscopic world of the atoms. Now, how big is this really, this number, this Avogadro's number? 1 mole of water molecules is about 18 grams, right? So we have 16 for the oxygen and 1 each for the hydrogens. That's just over a tablespoon. So you could easily hold that in your cupped hand, probably without even lapping onto your fingers. How many pieces would there be in that? Avogadro's number of pieces, of course. So let's compare that with a stack of paper. So we're going to take some paper, we're going to stack it, 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 stack it. All right. If we had if we had Avogadro's number of pieces of paper, how high would that be? If we do some calculations based on, a ream of paper is about 2 inches tall, and we just did some calculations, we would find out that our stack of paper would be 1.9 times 10 to the 16 miles. 1.9 times 10 to the 16 miles. How high is that? Well, a common way to compare things is, well, would that reach to the moon and back? Yeah. 43 billion times. So that is a long distance. And that's just if each atom were as wide as a piece of paper, is thick. And that's not very thick. Let's think about marbles. If we have Avogadro's number of marbles, would it cover the Earth? I mean, the Earth is a pretty big place. There's a lot of surface area on the Earth. It's hard for me to even imagine how big the Earth is when you look around. So would Avogadro's number of marbles cover the Earth? If atoms were as big as marbles, would they cover the surface? Yes, they would. 3 miles deep. So I can't even imagine 3 miles deep of marbles in one spot, much less over the entire Earth. So that's quite impressive. And that's, of course, kind of estimates, but rounding off. But it gives us the idea that that number of water molecules can fit in my hand. These are pretty small little guys. So the mole is useful because it's a unit that is big enough for us to actually see and use and be useful to us. Now, we get 2 relationships that are really useful out of this whole business that we will use going forward. The 2 relationships are, one is the molar mass. Molar mass is simply the mass of whatever it is that there is in 1 mole. So 1 mole equals X grams. By the way, the abbreviation for mole is MOL. You don't You can't use M because that's meters, and so unfortunately we're stuck with an abbreviation that's only one letter shorter than our actual name. But oh well, that's what we've got. So back to molar mass. 1 mole is however many grams. I just put X grams because it varies. We just look at the periodic table and we add up the masses that are listed. It's different for every substance. And so we just look at oxygen, and it says it's 16, so that's 16 grams in a mole. We look at helium, and it's 4, so it's 4 grams in a mole. And so it's really important to realize the units of molar mass are grams per mole. Okay. The other relationship that's really useful is the number of pieces, and a lot of times we don't need this one as much because we're not going to be dealing with individual pieces that often, but whatever pieces or entities that we have, 1 mole is equal to 6.02 times 10 to the 23rd of them. That doesn't matter whether it's atoms or molecules or formula units or ions. It's the same. It's always 6.02 times 10 to the 23rd. So molar mass varies with every substance. And number of pieces, that is the number of atoms, the number of whatever, that is the same for everybody. So a simple example of using this, if we had 14 grams of copper and we wanted to change it into atoms, we wanted to find out how many atoms are in that 14 grams of copper that I have. I'm going to use 2 conversion factors because I have these 2 relationships. I'm going to go from grams to moles, and then I'm going to go from moles to atoms. How many grams are in a mole? That varies. So I have to look up copper on the periodic table. 63.55 is what it says, so that's what I'm going to put. And for the number of atoms in a mole, it's always the same. It's 6.02 times 10 to the 23rd. If this were molecules, I would use the same number, but just with molecules. So now I can do my calculation, and I can come up with the number of copper atoms that I had in 14 grams.